Hello and welcome to Statistics here. We're going to look at in Chapter 10, building on what we've already discussed in Chapter 9 on our first introduction, moving from z-tests to t-tests. So the learning outcomes in this particular chapter include understanding the circumstances under which we would want to use within subjects design rather than control groups, because those are the two matched pairs designs that we would use the matched pairs t-test for. We're also going to, this is part of the homework, is to create a method for conducting a within subjects design experiment, coming up with an example for that. In addition, creating a method for conducting a matched pair design experiment. Now, I took out the actual conducting of one of these. That's something that we would have done in class. I actually had a test and we would take the test and all that. I'm just going to skip over that for right now. So what I'm going to do, similar to what I did in the other Chapter 9, is I'm going to go over the within subjects design options that we have and then the matched pairs. And we'll see, you'll recognize, I believe, some of the traditional ways in which psychological research is conducted, and that leads to the decision to use this kind of t-statistic to see if there's a significant difference. Now that's one of the things that we are going to be emphasizing in this particular area. Is what we have looked at before is the significance of a particular score as it relates either to a standard score, such as in z-tests, or to an approximation of a standard test that we see in t-tests. What we are looking now is at change. Now that's either differences between two groups or differences within a group. And you'll see where this is kind of where a lot of research happens. We have a group of people, they're at a particular depression rate right now. We introduce a new medicine and we measure their depression after. So we're looking not at a straightforward score, but how it changed from the precondition to the post-condition. Now that particular kind of design is the design we're going to take a look at first, and that is our within subjects design. So I'll continue to use that example of a new medication has been developed for depression, and as with all of our studies, we have a question about, can this medicine be effective for everybody who has depression, which is our population. So we take a sample, and we draw out that sample, and we first measure where are they right now in terms of their depression. This is the pre-test. So we might even use a standardized depression scale, but we're not going to necessarily, they already have the diagnosis. We may use the depression scale first to determine that they're a certain level of depression, and those are the people that we're going to sample, and we would do that by comparing it to standardized scores. But now that we're just dealing with our sample, we're going to say, what does this sample look like in terms of individual scores, in terms of the mean scores? Where is this group right now in terms of their level of depression? Then we introduce the treatment. We introduce the new medication. We wait for it to get to the blood level. We do all that stuff. And then we measure them again. And what we're looking for is a difference between the mean before and the mean after. Now, in order to do the statistical test for that, we are going to compare the means, number one, with mean number two, and we are going to be using the t-statistics matched pairs. Now that's the first way that we do it. Now the second way in which we do this particular kind of experimenting, the kind of before and after, is using a control group. And this may be very, very similar to you, but in terms of statistics, it's kind of the same. So we have one group here in this within subjects. We're taking the one group and we're measuring them twice. In the next research method, we're going to be taking two groups and we're going to be measuring them twice. And we're going to compare how much the groups changed. So let's take a look at that particular design. That is called the matched pairs design. And the way we conduct our research is we take two samples. Now, the first thing that we want to make sure is that these two samples are as similar as possible. They're drawing from the same people who have depression in our particular instances, but we want to make sure that any factor that we think may play into the results of our study is matched between these. So we select. So let's say we think gender might be a factor, then we make sure that both groups have the same proportions of the different genders. If we think that maybe age has something to do with it, or the number of years that they've had the diagnosis, or, we match the groups so they look very alike, because we're going to want them to be very alike, because we're going to submit one group, we're going to give them the treatment, and the other we're not. And the way that kind of plans out is we look at these two groups. One group, we take, well, actually, for both groups, we take the pre-test, where are each one of these groups in terms of their depression prior to doing anything. Then we take our test group and we give them the new drug, the experimental conditions or treatments. We subject them to that. And in the control group, we put them through everything the same. We bring them into the room, we talk to them about depression or whatever it is. We do everything the same except for giving the drug. The reason for this kind of design is because, unknown to us, we may bring a group in and the actual environment in which we are doing that, the actual talking to them about it, the actual, going through the procedure of getting the drug, may actually have an impact on our dependent variable, the drug being the independent variable, because there's all kinds of other variables, the day, the staff, or they like the staff, or anything like that. In fact, we can go so far, and this will be another familiar topic for you, we may go so far that the control group actually, let's say this is in the form of a shot, and so all the people in the red group received a shot with the medication in it. The other group received everything that was there, including a shot, but the shot was, let's say, saline solution, but we didn't tell them that. So that's called a placebo, where we inject a medicine, quote, but it's not really a medicine. It's duplicating every experience that the red group was going through in the blue group, but they just don't get the medicine. So what that allows us to do is any difference between this group, we can basically say, well, they both went through all this exact same experience, and the only thing different is the independent variable. Did they get the drug or did they get the placebo? And that helps us isolate the cause of any change that we would see. So it kind of factors out all of them, even the ones we don't know about, because we know the only thing in terms of everything that we did that was different was one got the drug, one got the placebo. So when we go into calculating our statistics, we retest each group, we get a mean for each one of them, and we compare the means, we compare the change, the difference between the pretest of the red group and the difference between the pretest of the blue group, and the current values that we have from, after the experiment. So these are the two experimental designs. If you're going to design something and you're going to test the same group more than once, That, like a test retest sort of thing. That's a within groups design, and you use a t-test for that. When you are going to take one group, expose them to treatment conditions, and the other group is a control and they get a placebo or whatever, then you're comparing the means of two groups. You're also using a t-test, but that's the matched pairs design. So that's the two research designs that utilize this level of t-test. Now, let's take a look at the math. Now, some of the math that's in here, first off, prior to this time in the last chapter, we were moving from the z-test to the t-test. We were still, now this was the ability to compare means, the ability to determine the score or the mean based on a standard, and that was the z-test. And then we were able to do that when we could estimate that standard using our sample data. So here we have the the equation on the right here, the t equals the equation, the mean minus the presumed or guessed average over the variance. Now, in this particular area, we're still looking at this equation, but what we've done, instead of looking at that mean, the x with the line over it, we're looking at the change. So we're looking to see if there's a big enough change before and after the treatment, regardless of whether we're doing it within groups or between groups, matched pairs. So we changed this to this particular equation, which the t equals the difference, that's what the d is for, minus the difference of the standard, and that's, get to that in just a little second, over the variance of the difference, that's the standard deviation there. And we know, and this is kind of an interesting piece here, we know that the d is the difference between means, and the standard, meaning the way we interpret that is there's been a change. If the null hypothesis is correct, then there's no change. So the average change that we use for the mu d is 0. So we substitute a 0 for 0 change because that's our null hypothesis. So either our treatment produced a difference within the group or in the matched pairs, or it didn't. And so the default, the null hypothesis is always there will be no change, therefore the average change is 0 under those conditions. So we can substitute that 0 right in that equation when we're doing this kind of thing. So at this point, if we were in class, we would switch over to class activities. There's no labs for chapter 10, but I do want to go through the actual labs that are in there. So we're going to be looking at lab 31, which is related samples t-test, and doing some of that in SPSS, and then doing some more. Lab 32, related samples t-tests in SPSS. So let's take a look at those particular labs. I'm going to bring them up here. So we're going to start off here with lab 31. And here we have lab, I'm going to bring this right up here. Here's lab 31. This is my answer sheet. Now keep in mind, this is not to be submitted. This is for you to do the work. So stop the video right now and go do lab 31 as best as you can, and then come back, and then we can talk about lab 31, and then we're going to do the same thing for lab 32. Hello. Okay, so we're going to launch into lab 31. So let's take a look at lab 31 right now, and the first question that we're given here has to do with a college or university has the tarnished image. They put together a short television commercial and showed it to 7 people, and they measured the attitudes of those 7 people before and after. So you're looking at 7 people designated by A through J. This is their score, the 15, 11, 10, 15, 11, 10, 11, 14. That's the before score, and here's the after score. In between there, they had the subjects look at the video. So this is a within subjects study. So they're looking at the same people, measuring them twice. So that's the answer to the first question. We go down here, and we're like, within subject design, the same people are being tested twice. Now, if we're going to go into the steps that are outlined on page 201, and we were going to walk our way right through the design of this experiment, and I'm going to use SPSS to compute the t-score. So we'll look at my answers here, see if you came up with the same thing. So here we have step 1, state the hypothesis, and the experimental hypothesis, or H1, students will rate the college higher after watching the video. That's what I think, that's what we hope. HO, which is the null hypothesis, there will be no change in the students' rating of the college after watching the video. So that's what you want to write down for your hypothesis. Your decision criteria, we're going to go for the alpha equals 0.05, or there's a 5% chance that we want this beyond that 5% chance of happening by chance. We collect the data, and that's what we have up here, and we calculate this in SPSS. So, and then we're going to make a decision about it. So this is lab 31 here, and I have my databases here. I have actually all the data. If you look at this page right here, I have the data for one question, the data for another question, and other data for another question. And SPSS has that really, you just put it all on one table here. Looks just fine. And the data that we are looking at is this first one right here, and I actually am missing one here. This is 18. That was that last. So this data right here matches this over here. Right here's that data that came out of the lab manual, and here's this. So we want to calculate the t-score on these. So for the before and after, and so to do that, I go to Analyze, and I go Compare Means, and I go to Paired Samples t-test. And interestingly, when we're using the Paired Samples t-test, you have to remember the equation that we're looking at the difference between the after and the before. So when you're entering in the variables, you want to put the after as variable 1 and the before as variable 2. And the way that looks, it's a little confusing, but I want the after, I pick after and I pick that, and it goes into variable 1 right there, and I pick before and I go into variable 2. So it's going to take that and subtract that. That's going to be the difference that it's going to make. So I press OK, and the results come up here. And you'll see you get the statistics here, the if there's a correlation between them, those kinds of things. But down here is your t-test, the paired samples t-test. You have the mean, standard deviation, standard error, the confidence levels right there. T is 2.976 with a degree of freedom of 9, which gives us a two-tailed significance of 0.016, which is not quite at the 0.01 level of confidence, but it is certainly way below the 0.05. So yes, This is significant, and right there you can see the T. This is how it gets reported. T with the degrees of freedom of 9 is 2.976. The probability that that occurred by chance is really low, 0.01 or 1.6%. Plenty of cool stuff there. Plenty of good data. Okay, so that's the answer to the first question. The second question actually takes a look. You can see the answer there, but I'll show you how I got it. It takes these different scores. Now this is kind of rushing to the data. It's already done the difference between the first set of scores and the second set of scores. Now this is just one set of scores. And the interesting thing about when you know the differences between the first set of scores and the second set of scores, you can actually do a one sample t-test like we did in chapter 9 on those differences. But because you're doing them on differences, you're going to get the correct answer as if you did the paired samples tests. So for that particular lab, I took those numbers and I put them right here in these differences. Now I'm going to do another analysis, so I go and analyze, compare means, but I'm going to do a one sample t-test because it's just a set of differences. So doing a one sample t-test of the differences is the same as doing a paired samples t-test when you have the raw scores. It just does the math for you. Okay, so back to that, we look at our one sample t-test. The variable that I want to look at is the differences. So I bring that over. It's right there. The test value is 0. Remember, when we're looking at differences, the null hypothesis is that there's no difference. So I want to see if there's anything other than 0 difference. And I press OK. And there's the previous analysis here. It just, when you're working in SPSS and you're doing repeated analyses, it just adds it to that output sheet. They all just pile up on top of each other. You can see the first test I did right there, the second test I did right there. And in the second test, this one sample t-test, here we have a t of 12. This is way high, degrees of freedom at 8, with less than 0.000. This is extreme results. There's very strong results, less than 0.001. That's how you would probably report it. So we look back here and I say, yes, there is a difference between whatever it is consistently across those scores. T with 8, oh, I'm sorry about that. Yes, there's a difference. T with 8 degrees of freedom is 12, and P is less than 0.001. Now we go into another study here where we're looking at handedness and we're comparing twins. These are matched pairs. Doesn't matter. We're still going to use the same t-test. So we go in there, and because they're the same, we're assuming they're sort of the same because they're matched in this way, you know, twin A and twin B. So here we have 6 pairs. We have scores over here, and we have scores over here, and we're going to determine whether there's a genetic determination of handedness. And we go up here into SPSS again, and I put the data in there. So there's twin A and twin B, and we're going to do the same test that we did over here. We're going to analyze, compare means, paired samples. Let's get these out of here. It's still remembering my last one. Kind of, you could actually do them all. You could have done the before and after, and then you could have done the twin A and twin B. Remember here, you put the twin B into variable. It might not matter on this one. Before and after. Oh, I don't want before. I want twin B. There, twin B and twin A. Make sure you don't do that. And I want to calculate the statistic for that. Again, it piles it up here down at the bottom here. We have our paired samples. We have it, look down here, the T of 2.108, degrees of freedom 5.089. So what we conclude is because 0.08 is a bigger number than 0.05, then this is not significant. It's not a big enough connection to say that handedness is genetic. There is just as likely for them to be having, left-handed and right-handed, even though they were twins. Okay, so moving right along, we go to this next place right here, and we see this information. What we're given is the information about that we can stick into the equation. And for these two right here. Now, we're going to find the t values, and we can, without looking up the critical t, can you tell which one of these is more likely to reject the HO? And I just want to point out for critical thinking that N of 10 and the differences between the scores in that group is +4. N of 10 and the differences between those is +4. So they're the same in those regard, but the standard deviations are higher. There's much more variability in this group. So that group is less likely to reject the HO because it has such high variability already. So if we were going to actually compute the t values, we can do that by hand. And to demonstrate that, I'm going to use my handy dandy little iPad. So here we are with the first equation, and we have n is 10 plus the degrees. The differences is 4.0, the average difference, and the standard deviation is 2. So we would substitute these into that equation. So t would equal 4 minus, now this part right here, that becomes a 0. 4 minus 0 over, now we're looking at this part, which comes right from there, so that's going to be 2 over the square root of n, which is 10. So we solve that, and what we end up with is, for that particular group, t equals 6.35. So go back into here. So this equals 6.35. That's a pretty high t. I could probably tell already that that's going to be a significant. Now, let's go to the next equation here. We do exactly the same thing. We have t equals the difference, which is 4.0, I guess, minus 0 over the standard deviation this time is 2. Oh, did I get these right? Oop, I did the same standard deviation. Sorry about that. I'll make the second one. This is 10. 10. Okay, so that number is 10 over the square root of 2. Don't you love it when math instructors make mistakes and it just gets so confusing? I apologize for that. So here we are, we're just substituting these values into this equation. And when we do this equation, where there's a much larger variability, we're going to end up with a score of 1.27, which is not a really high T. It's kind of like the Z's, you know, it's number of standard deviations. T's are sort of like that too. So it's not really, you have 6 point something, obviously a very significant difference because the actual data is not as varied, so the changes move together like that. So much more significant result. So little hand calculation there going into this, and that brings us to the end of Lab 31. Now, Lab 32, right here, I'll get that going. Lab 32 is a straightforward related samples t-test. You have person 1, person 2. This is a person, an instructor teaches statistics. She wants to know if her lectures are helping her students. Like, I would want to know if this video is going to actually help or not. Same sort of data collection. There's only 2 of you, so I can't really get any data on that, but kind of funny that that's what the example is. So we have 10 samples. We have before and after scores. This is before and after the lecture. So we're going to see if that makes a difference. So we take all this information. Let's get into SPSS here. Here is the SPSS. There's the before scores. There's the after scores. And then I want to compute. I go to Analyze, Compare Means, Paired Samples t-test. I'm going to do the after. Remember, we want to put those backwards. The after goes into variable 1. Before goes into variable 2. And then I press OK. And right here, this last paired samples test, we have a T of 2.281, a degrees of freedom of 9, and 0.048. Yay! Yay for lectures. This is less than 0.05, so therefore it's significant to the 0.05 level of confidence. So again, that language being, there's only a 4.8 chance. I'll use the word probability. There's only a 4.8% probability that the instructor got these better results by chance. Now, just like we did that in Lab 31, we did an experiment and when we had the differences. Now, in SPSS, I just did it manually, but I just created a column over here with the differences. You can actually have it calculate that for you. But these are the differences in score. This one, student A had no difference. Student B went up 2 points. Student C went up 8, up 2, up 4, 0. One person went down. That's bad. One person went up 10, 1, and 3. And now we can do a one sample t-test on the differences, just like we did that one sample t-test on the differences scores in Lab 31. So let's take a look at that. I go into Analyze, Compare Means, one sample t-test, but I'm going to look just at the differences. I move those over there. Remember, the test value is 0 because no differences is the null. So that would be the change. That would mean there's no differences. And then I press OK. And I have a T of 2.389041. And look how similar those are. Now, there's always some loss of data when you're looking at different, the differences and whatnot. But you look, they are very close. They're very close. Of course they're very close. You're looking at the exact same information. And for all I know, that little difference there might be because of a typo. So that tells you that doing a one sample t-test of the differences, the actual differences between the scores, the same as doing a paired samples test of the original data. So that is it for the labs, the practice labs. The homework focuses on some questions and creating some designs to actually use within design, and then matched pairs, when you have like a control group or something like that. So good luck with all of that. I hope this is, again, hopefully it's a helpful video, and I will see you next time.